Hello, and welcome to our single cycle CPU presentation. So first I'd like to begin to explain our data path and how it differs from the data path given in the project, what was it called, PowerPoint. And so at the bottom here we have the opcode. Normally it went into the PC control and the ALU control, and based on the opcode it did its operations, but instead we have all the opcode going directly to the main control and having slight control signals from the main control going to the PC control and the ALU control. Everything else is pretty much the same. We have the PC counter, it's selected by the multiplexer. It chooses the instruction, it chooses the registers or the immediates that will be used, and sends it to the ALU. Or, if it's a jump command or a branch command, it'll send it back to the multiplexer for the PC control, and it'll directly send it into ALU, which will go back to the registers if necessary. And so we can do a lot of instructions already at this point. So going into the actual logism file, here's our PC control, where it adds for every command unless given the PC source, which changes it to either the 16 immediate or the 26 immediate, which we have extended right here. Then it goes to the instruction register, it gets the instruction address from the PC control, and outputs the instruction right here, which will also go here. Here's where the instruction is pretty much dissected for everything it holds. It takes out the opcode, sends that to the main control. Here's the register 1. Here's the two registers that are chosen by the multiplexer, if necessary. Here's the immediate 16, immediate 26, and the function used by the ALU control. So the next step is going to the register, because the register is pretty much the next step. It selects the register. The register 1 is always used. It selects which register will be written to or looked at next, and this all depends on the main control, which has the opcode by now and selects the appropriate control bits. The output is sent either to the memory or the ALU, and I believe that's what's chosen. There's another multiplexer that chooses whether or not it will go into the memory or not, and written back to the register, sorry. The next step is the next clock cycle is ticked and another instruction goes through. So here, let us look at our main control unit. We have all the different types of instructions we have. Our types are the 00000 opcodes, and we have it selecting the appropriate control unit. We use this with, I think it's called a PROM or ROM, one or the other, but it's similar, very similar to this. Then we have those control signals go to the ALU control. Here it is. And if there's any ALU signals from the main control at all, it would automatically select those signals over whatever the 16 immediate, the last 16 immediate give. So it'll automatically choose these if it's not an R type. And then finally we have the PC control, which it gets the PC control signals from the main control again, and is sent to our PC source, which controls the multiplexer that's used. So finally is actually running code on this. So unfortunately, how the register is set up, you kind of have to input the code manually, and that takes a second. So please bear with me while I explain. So every one of these clocks, it'll store the code if this is selected. This is the manual input, which normally you wouldn't have to deal with. In a logism file, you could right-click edit, but how our memory is set up, it uses like banks of modules of circuits, banks of modules of chips, excuse me. And it's kind of confusing to get to the right address, so we have to input it this way. So what I'm planning on doing is adding 63 to a register, and then adding 1 to a different register, and once those are equal, it'll do nothing. Like, it'll get out of this loop. It'll keep looping until this increments to this register. So that is the ultimate goal here. So let me input those instructions first. So add I at R2. Maybe not 63. I've tested this previously, and it took a long time to get to like 16 already. But that was me manually clicking. So let me try a bigger number. And I have a little viewing window down here for the register 1, register 2, and the instruction address we're currently at. So you can see the jumping in action. Clock. So what happened just now is it was stored at the instruction address of all zeros, and then we went to the next instruction address at 4, and now I have to store the next command. Oops, wrong. So now we're adding the 1 to the register 1. So this is pretty much an increment command. So I clock it, stores. Now we're doing the branch on equal. So if R2 and R1 are equal, it'll just skip 4. So ideally, instead of going to C after, which will jump back, it'll go to 10, which is, of course, hex. But this next command for BEQ is... Then I'll store that. And then lastly, we have the jump command, which is simple. Oops. And it jumps to 4. So clock that. So we'll stop storing for now. We'll get this ready. This is the value that kind of stores. I don't know, it's kind of weird. Our single cycle CPU kind of only has 2 cycles. That's funny. It's called a single cycle. So if we reset this, it'll be pointing at register 0. And nothing has been written yet, but everything's in place to be written once that second clock ticks. This is the value that'll be written to our register 2, I believe. And that is in preparation for, here's register 1, here's register 2. Once they're equal, this should keep going and incrementing past 8. No, past C. C is where it stops, I believe. So instead of me clicking this for approximately 128 times, I'm going to hit ticks enabled and then speed it up a little. But you should be able to watch the registers increment. Oh, look, this is why it's not incrementing, is this reset button is currently hit. So once I stop that, it should increment now. And let me speed this up a little. And notice how these 3 are just looping. That's because it's stuck in a loop currently and the address is just resetting. It's a little too slow still, so let me speed it up by 2. Well, it's doing what it should be doing. It's currently incrementing by 1 every time. Let's double it again. We're trying to get to this number right here. So we're about halfway there. And then once it reaches this number, this should start continuing because it's just the instruction address. It's out of the loop. All right, it works. But now everything's frozen. All right, and that was our, little demo of our single cycle CPU.